His calloused hands gripped the rope, muscles straining against the weight of the massive beam. Snow was already falling, and winter in the Japanese Alps showed no mercy. A family of 12 had two choices: raise the roof before the blizzard hit, or watch their home collapse under tons of snow. It took generations of knowledge, an entire village working as one, and timber joints so precise they locked together like interlaced fingers. Because in the mountains of Shirakawa-go, a house wasn't just shelter, it was a fortress against nature's deadliest weapon. But how did these mountain families do it? How did they build structures that could bear the weight of snow deeper than a man is tall, using nothing but wood, rope, and centuries of inherited wisdom? How did they create homes that would flex and bend but never break, even when buried under the equivalent weight of several automobiles? That's what we're here to find out. From timber in the forests to stone in the mountains, every culture built to survive. This is Timber and Stone. Part 1. The Praying Hands. For over 800 years, the steep-roofed houses of Shirakawa-go have stood like monuments to human ingenuity. But their story begins not with triumph, but with tragedy. The Japanese Alps receive some of the heaviest snowfall on Earth. In the village records of 1837, scribes documented what they called the Great Burial, snow depths of over 20 feet that lasted for months. Families who built wrong didn't just lose their homes. They lost everything. Entire bloodlines vanished beneath the white silence. The survivors learned. They had to. The Gassho-zukuri design emerged from this brutal reality. The name means praying hands, and when you see the steep triangular roof rising 60 degrees into the sky, you understand why. But this wasn't about prayer. It was about physics, refined through generations of trial and deadly error. Picture the problem these mountain families faced. Snow doesn't just fall, it accumulates with relentless patience. A flat roof might hold a few feet before buckling. But 20 feet of snow? That's the weight of a dozen cars pressing down on your home, hour after hour, day after day. Traditional Japanese architecture, with its elegant curves and gentle slopes, would collapse in hours under such impossible loads. The solution was radical. Build a roof so steep that snow couldn't grip it. At 60 degrees, fresh powder would slide off like watered-down glass. But the engineering challenge was staggering. How do you build a roof that steep without it collapsing under its own weight? How do you create a structure that can flex with massive loads while maintaining its integrity? The answer lay in an ancient Japanese principle that would revolutionize their survival: sashimono, joinery without nails. Every beam, every rafter, every support post was connected through precise wooden joints. No metal fasteners that could rust, corrode, or fail under stress. No weak points where forces could concentrate and tear the structure apart. Just wood against wood, locked together in a three-dimensional puzzle that actually grew stronger under pressure. The main support beams, called ushibari, ran the full length of the house, sometimes stretching over 40 feet without a single joint. These weren't just logs pulled from the forest. They were carefully selected trees, aged for years in specific conditions, shaped by master carpenters who could judge the grain's strength with a single glance. Each beam was connected to its neighbor through complex joints with names that carried the weight of centuries: the kanawatsugi, the aritsugi, the hozotsugi. The kanawatsugi joint was perhaps the most sophisticated. Named after the metal rings that bound wooden buckets, this joint created a mechanical lock that prevented any sideways movement. The carpenter would cut a precise mortise and tenon, then add interlocking wedges that could only be assembled in one specific sequence. Once locked together, the joint was stronger than the wood itself. But the real genius was in the roof's flexibility. Unlike rigid structures that fight against stress until they shatter, the Gassho-zukuri roof was designed to move. As snow loaded one side, the entire frame would flex slightly, like a tree bending in wind, distributing the weight across the whole structure. It was architecture that breathed with the mountain, that danced with forces that would destroy lesser buildings. The precision required was extraordinary. Each joint had to be cut to tolerances measured in fractions of inches. Too loose, and the structure would sag and fail. Too tight, and the wood couldn't move naturally, leading to cracks and eventual collapse. Master carpenters spent decades learning to read wood grain, to understand how different species would behave under stress, to predict how joints would age and settle over time. The wood selection process was almost mystical in its precision. Carpenters would examine trees in winter when the sap was down, looking for specific grain patterns that indicated strength. They preferred trees that had grown slowly on north-facing slopes, where harsh conditions created dense, resilient wood. The best timber came from trees that were at least 200 years old, their grain tight and stable from centuries of mountain weather. The testing of wood was ritualistic. Master builders would strike potential beams with wooden mallets, listening for the clear, bell-like tone that indicated solid, uncracked timber. They would examine the end grain under different light conditions, looking for the tight, even rings that spoke of slow, steady growth. They could even smell the difference between strong wood and weak wood, detecting the subtle chemical signatures that revealed a tree's health and strength. Modern engineers struggle to replicate this level of structural integration, even with computer modeling, steel reinforcement, and advanced materials. These mountain craftsmen achieved it with hand tools, inherited knowledge, and an understanding of wood that bordered on the mystical. Part 2. The village raises a roof. Building a Gasho-zukuri house wasn't a family project, it was a community event called Yui. When one family needed to raise their roof, the entire village responded. Because in the Japanese Alps, survival was a collective effort, and individual failure meant community death. The process began months before construction, sometimes even years. Master carpenters would walk the mountain forests in specific seasons, selecting trees not just for size, but for character. They looked for straight grain, minimal knots, and wood that had grown slowly in harsh conditions. Fast-growing timber was weak timber, prone to splitting and warping. Mountain wood, stressed by wind and cold, developed the density and strength needed to bear impossible loads. The selection process was almost ritualistic. Carpenters would examine the bark patterns, feel the wood's weight, even smell the sap to determine quality. They knew which slopes produced the strongest timber, which elevations yielded the most stable grain, which seasons provided the best cutting conditions. This knowledge was passed down through generations, refined through centuries of success and failure. The felling itself was a ceremony that could take days. The entire community would gather to witness the cutting of the main beams. Special prayers were offered to the mountain spirits, asking permission to take the trees. The first cut was made by the master carpenter using a ceremonial axe that had been blessed by the village priest. Only then would the other workers join in, their saws and axes working in rhythm as the giant trees slowly surrendered to human will. The timing of the felling was crucial. Trees cut in late fall or winter, when the sap was down, would be stronger and less prone to insect damage. The phases of the moon were considered. Wood cut during a waning moon was believed to be more stable and less likely to warp. These weren't mere superstitions, they were observations refined over centuries of experience. Once felled, the logs underwent a process called shiage, careful shaping and preparation that could take months. Using tools like the yarigana, spear plane, and the chona, adze, craftsmen would shape each beam to precise specifications. No two pieces were identical, but each had to fit perfectly with its neighbors in the final structure. The chuna work was an art form in itself. This curved adze, wielded with both hands, could remove wood in precise, controlled cuts. Master craftsmen could shape a beam to within a hair's breadth of the required dimension, creating surfaces so smooth they seemed polished. The rhythm of the chuna was almost musical, dozens of workers moving in synchronized strokes, the sound echoing through the mountain valleys. The wood was seasoned through careful drying processes that took into account the mountain's harsh climate. Logs were stacked with spacers to allow air circulation, protected from rain, but exposed to wind. The drying had to be gradual, too fast, and the wood would crack, too slow, and rot would set in. Master builders could judge the moisture content by the sound the wood made when struck, by its color, by subtle changes in weight and flexibility. The raising itself was a choreographed dance of dozens of workers that could last for weeks. Picture the scene. 40 men lifting a beam that weighs as much as a small car, guiding it into position with ropes and wooden levers. One mistake, one moment of poor coordination, and someone could be crushed beneath tons of timber. But this wasn't just about muscle. The UI system represented something deeper, a social contract written in wood and rope. When your neighbor's roof needed raising, you dropped everything to help. Because next season, when your own house needed repair, those same hands would be there for you. It was insurance written in sweat and solidarity. The coordination required was extraordinary. Each worker had a specific role, from the master carpenter who guided the main beams into place, to the young apprentices who managed the ropes and pulleys. Commands were given in a special vocabulary developed specifically for construction, words that could be heard clearly over the noise of work and wind. The master carpenter would call out, "Yoisho," and 40 men would lift as one. "Migi," and the beam would shift right. "Tomete," and everything would stop. The women played crucial roles too. While men handled the heavy timber, women prepared the thatching materials, bundles of Suzuki grass and bamboo that would form the roof's weatherproof skin. They also managed the complex logistics of feeding dozens of workers, coordinating materials, and maintaining the social bonds that made UI possible. Children learned by watching, their small hands gradually mastering the knots and joints that would one day save their own families. They started with simple tasks, sorting materials, carrying tools, preparing food. But they were absorbing something more valuable than technique. They were learning that survival was a community effort, that individual strength meant nothing without collective cooperation. The entire process, from foundation to finished roof, could take weeks. But when it was done, the result was more than a house. It was a testament to what humans could achieve when they worked as one, a physical manifestation of social bonds that could withstand any storm. Part 3. The Flexible Fortress. The secret of Gasho Zukuri wasn't just in the steep roof. It was in how every element worked together as a living system. Think of it as a wooden organism that adapted to survive, each component serving multiple functions in an integrated whole. The foundation started with massive stones called ishibakachi, carefully selected river rocks that could bear enormous weight without shifting. But unlike Western foundations that fight against ground movement, these stones were designed to move slightly, absorbing the shock of settling snow and seasonal ground shifts. The stones were positioned with gaps that allowed for thermal expansion and contraction, preventing the rigid failures that destroyed less flexible structures. The selection of foundation stones was a specialized skill that took years to master. Master builders looked for rocks with specific characteristics: dense granite or basalt that wouldn't crack under pressure, shapes that would interlock naturally, surfaces that would grip the wooden posts without crushing them. Each stone was tested by striking it with a hammer, listening for the clear ring that indicated solid, uncracked rock. Above the stones rose the main posts, thick columns of keiyaki, Japanese zelkova, or other hardwoods that formed the house's skeleton. These weren't simply vertical supports driven into the ground. Each post was connected to its neighbors through a network of horizontal beams and diagonal braces, creating a three-dimensional framework that distributed stress in all directions. The posts themselves were works of art. Selected from trees that had grown slowly in harsh mountain conditions, they were shaped to precise dimensions using only hand tools. The base of each post was cut to fit perfectly on its stone foundation, while the top was carved with complex joints to receive the horizontal beams. No two posts were identical, but each was perfectly suited to its specific role in the structure. The walls themselves were secondary structures built to flex with the frame rather than resist it. Made from woven bamboo and packed with clay and straw, a technique called tsuchikabe, they provided insulation and weather protection while allowing the main structure to move freely. The walls could crack or even partially collapse without threatening the building's integrity. The tsuchikabe technique was refined over centuries of experimentation. The bamboo lattice had to be woven in specific patterns that would hold the clay mixture while allowing for movement. The clay itself was mixed with chopped straw and sometimes animal hair, creating a composite material that was strong in compression but flexible enough to accommodate the building's movement. But the real engineering marvel was in the roof's internal structure. The rafters weren't simply nailed to a ridge beam like in Western construction. Instead, they were connected through a complex system of interlocking joints that allowed each rafter to support its neighbors. If one beam began to fail, the load would automatically redistribute to adjacent members, preventing catastrophic collapse. The ridge beam itself was a masterpiece of engineering that could take months to prepare. Running the full length of the house, it had to support not just its own weight, but the combined load of all the rafters and the snow they carried. The beam was often made from a single massive log, carefully selected and shaped to precise specifications. The thatching itself was another layer of engineering sophistication. Bundles of grass weren't just laid randomly, they were woven together in overlapping patterns that shed water while trapping insulating air. The thickness varied from bottom to top, creating a gradient that managed both water flow and thermal performance. Inside, the house was organized around the irori, a sunken hearth that served as the home's thermal and social center. But this wasn't just a fireplace. The irori was positioned to create convection currents that drew smoke up through the thatched roof, naturally ventilating the space while providing heat. The placement was calculated to maximize heat distribution while ensuring proper smoke evacuation. The smoke itself served multiple purposes beyond just carrying away combustion gases. As it rose through the thatch, it deposited tar and other compounds that preserved the grass, extending the roof's life and creating a natural pest barrier. What seemed like a simple fire was actually a sophisticated environmental control system that managed temperature, humidity, air quality, and structural preservation simultaneously. Modern passive house design is just beginning to understand principles these mountain builders mastered centuries ago. Integrated systems, natural ventilation, thermal mass, flexible structures, all achieved without a single piece of modern technology, powered only by human ingenuity and deep understanding of natural forces. Part 4. The Winter Test. When the snows came, the true test began. A Gashozukuri house didn't just endure winter, it transformed with it, becoming something new and stronger. As snow accumulated on the roof, the structure would gradually settle, the wooden joints compressing slightly under the immense load. But this wasn't failure, it was design. The joints were cut with precise tolerances that allowed for this compression while maintaining structural integrity. The house was literally designed to shrink under load, then expand again when the weight was removed. The steep roof angle meant that most snow would slide off in controlled avalanches, but what remained created an additional layer of insulation. The house became wrapped in a blanket of snow that helped maintain interior temperatures even as outside conditions reached deadly extremes. The snow acted as both insulation and thermal mass, moderating temperature swings and reducing heating requirements. Inside, families developed routines that worked with their architecture rather than against it. The irori fire was never allowed to die completely, not just for warmth, but to maintain the convection currents that kept the house properly ventilated. Smoke that might seem like a problem was actually essential for the system to function, carrying moisture and stale air up through the thatch while drawing fresh air in through carefully designed gaps. The multi-generational layout of the house reflected the realities of mountain survival. Grandparents occupied the warmest spots near the fire, their experience valued as much as their need for comfort. Children slept in protected alcoves, safe from drafts but close enough to the adults for protection. Working adults took the positions where they could respond quickly to structural problems or emergencies. The house became a microcosm of mountain society. Everyone had a role, everyone contributed, and everyone's survival depended on the group functioning as a whole. The architecture enforced cooperation. There was no privacy, no individual space that didn't affect the whole. It was communal living by necessity, but it created bonds that could withstand any hardship. When spring arrived and the snow began to melt, the house would gradually return to its original dimensions. The wooden joints would expand, the frame would lift slightly, and any minor damage from the winter's stress could be identified and repaired. This cycle repeated year after year, decade after decade, each winter teaching the structure new lessons in flexibility and strength. Houses that were built in the 1600s were still standing and functional in the 1900s, a testament to engineering that worked with natural forces rather than fighting against them. Some structures survived for over 300 years, sheltering dozens of generations through countless winters that would have destroyed lesser buildings. In the mountains of Shirakawa-go, a house was never just shelter. It was a covenant between human ingenuity and natural force, written in wood and rope and sealed with snow. These houses didn't just survive the snow, they became stronger because of it. And maybe that's the real lesson. Bend, adapt, endure. Thanks for joining us on Timber and Stone. If you want to see more stories of incredible survival engineering, make sure to subscribe and hit the notification bell. We'll see you next time.